Last time we got to see the new CNC router moving under its own power, and it was awesome. This time we're going to tune the ClearPath servos and make it even awesomer. Welcome back to Cloud 42, I'm James. Well, we got the new CNC machine running under its own power last week. We got the ClearPath motors adapted and installed on the machine. We got everything wired and programmed and got it moving, and the performance was everything I had hoped it would be so far. Now, we still have not tuned the motors for the particular mechanical loads and inertia that this machine presents, and that's what we're going to work on this week. We're going to go through the ClearPath motor tuning process, get everything tuned and running, and we'll talk a little bit about the techniques required to tune a machine with a dual drive gantry axis. A servo like this ClearPath consists of three basic parts. You've got a driver, you've got a motor, and you've got an encoder that keeps track of what the motor is doing and feeds that information back to the driver. So the driver takes commands from the computer telling it where to move the motor. It then generates current in the coils of the motor to actually move it, and then it reads the feedback from the encoder to see what the motor's actually doing so that it can then adjust to get the motor to actually do what you commanded it to do. Now, the control algorithms in the ClearPath in particular are relatively sophisticated. They're trying to compensate for the inertia of the axis, the friction in the axis, acceleration and deceleration. I believe they're actually trying to compensate for resonance in the axis as well, and they're trying to do that with a bunch of complicated, basically PID control loops. But in order to get that to work well, you have to tune the parameters for those control loops for the particular mechanism that it's attached to. If you add a bunch of additional weight, or if you switch between a screw drive and a belt drive, it's going to change the torque curve that's required from the motor to get a particular kind of motion. And so you have to tune those parameters. Most servos, most inexpensive servos that you buy, have software that you can connect, and you can go in and adjust those parameters and tune it yourself. Some of the more expensive options, like the ClearPath, come with software that allow you to automatically tune it. You just hook the motor up to the mechanism that it's going to be running, tell it, how much freedom it has to move, and then it will move the motor and explore the power curve and the motion of the machine and the resonance and the acceleration, deceleration, inertia, and it'll figure that out and automatically configure those parameters in the motor. And from my understanding, most of the time that works great. There are some situations where you may have to tweak things by hand, but in general, it will get you really close and certainly get you better than the parameters that are in the motor from the factory. Now, the challenge on a machine like this is that it has a dual drive gantry. So there is an axis on each side and there's a motor on each side, and they work in unison to move this gantry back and forth. And so I can't just hook the software up to this motor here and tune it, because it's going to try to move the gantry back and forth, but it's only turning one of the motors. And they don't have a provision for tuning the motors on the two sides simultaneously, so you're pretty much stuck tuning one at a time. You could disconnect everything so that it's free to move one side, but now you've changed the mechanical system that you're tuning. So the general approach is to simulate the inertia of the axis so that you can tune it and then copy the parameters to the other motor. On a machine like this, the two y-axes and the x-axis are essentially the same. They have the same ball screw, they have the same bearings. The only difference really is the amount of mass that they're moving. So the general approach is to put additional weight on the x-axis so that it's carrying the same amount of weight that one side y-axis will see, tune that, then copy those parameters to the other motors. So when I built this machine, I was careful to weigh every single part before I put it on here, and I have that data so we can figure out how much mass we need to add to the x-axis to simulate the behavior of the y-axis and do the auto-tuning. These are the weights that I recorded while I was building the machine, and all of this is in pounds because that's what my scale measures and that's what I have to load the machine up with. The side plates are 9.5 pounds each. There's two of those. Gantry extrusion was 20 pounds. The axis was 26. The Z-axis the bolt's on is 20. The spindle mount, a little under 4 pounds. The spindle, I think I remember it's 28 pounds. We'll have to check it when I actually get it off of the other machine, and if it's significantly different from this, it might require retuning, I'm not sure. Servos are 6 pounds a piece. There's 2 of those, one for the Z and one for the X that are on the moving gantry. We've got the servo brakes, 4 pounds, and I just estimated a couple pounds for a tool holder and tool and maybe 3 pounds of cables. So all in all, that's 137.6 pounds, and half of that would be 68.8. So half of that would be the amount of mass that on average is being moved by the motor on each side of the gantry. So that 68 pounds or 68.8 is what we would need to load onto the x-axis to replicate the behavior of the y-axis. So we are going to have the z-axis mounted on there. So there's already going to be 20 pounds mounted on because the z-axis is there, and the z-servo is up there. That's another 6. The brake is up there. That's another 4. That's a total of 30 pounds that are already mounted on there. We just need to add another 38.8, call it 40 pounds, and then we should be able to run the tuning on the x-axis, and then that should be appropriate for the 2 motors on the y-axis. So we need to add 40 pounds to the x-axis, and the way I plan to do that is just bolt some weight plates into the T-slots here. And to do that, I made some 1/2-13 studs that have M8 threads on the end so that I can use those with T-nuts to go in here. So let's start by giving us something to hold the weight of the plates while we're working. Get my clamping hardware and a couple of T-nuts. Okay, I need 40 pounds. Okay. Okay, that is 40 pounds on the z-axis. Let's start up the software and see what we can do. Okay, so the software comes up, says it is unconnected. So let me grab a USB cable here and plug into this motor. Now I do have the power supplies on, so it has 72 volt power, but it's not enabled. Okay, starting, and it's going to come up and tell me that it needs to be tuned, that it has no load mechanics connected, and I'm going to choose auto tune the motor. Click next. And yes, I've read these things are really powerful and they can move fast, and so of course there's a warning here to let you know that you could get hurt if you're not careful. So yes, I've read it. Okay, and you can set a torque limit. I'm going to leave it alone. I'm not actually going to change that, leave it at 100%. The peak torque on this motor is 1,600 ounce-inches, which is almost 11.5 Newton meters, which is really quite a lot. Click next. It will make some fast moves. It has speed limitations, 780 RPM. Yep, that's fine. And I do have limited rotation, so I'm going to click next here. I want to move the mechanics by hand, unpowered. Next, and now it wants me to move the axis through its range of motion. And I'm going to move it through most of its range of motion. Now I believe it's only going to be using like 90% of whatever I moved here, but I'm not moving it clear to the end because I'm chicken. Because once again, these motors are very powerful. Click next. Okay, next. Now it's warning me that I may hear all kinds of noises while it's operating and that that's perfectly normal. And you can always press the escape key at any time to stop the process. Okay, I'm going to click run, and then I'm going to keep my hand near the escape key. You can see it's just starting to barely move a little bit left and right, and it's going to slowly work up the torque until it figures out what the limits are. You can hear the slats in the plasma table rattling. Okay, auto tune says it's at 100%. I'll click next, and I will go ahead and disable the motor. The reason they have this here for the disable is so that you can move it to a position where you want it to be before you disable it, but I'll go ahead and just click disable. Okay, next. And there are fine tuning parameters, but I'm not going to worry about those right now. You can go in and change the fine tuning parameters to make the motor hold position better, but with more noise, or to be quieter without it working as hard to hold the commanded position. I'm just going to leave it at the default, and we'll see how that turns out. I do want to change the motor identity settings, and I'm going to name this Avid Y axis, and make a note here what this is, what I did, and click OK. Okay, now what I'm going to do with this, I'm going to go to File, and I'm going to say Save Configuration, and I'm going to save this onto this machine, and this will be the Y-axis ClearPath configuration, and we will save that. Okay, so now I have that tuned in the X motor, and I've actually saved those parameters. So now I can pull this out, and I can go over here, plug into one of the Y motors after rotating the USB connector into the correct position. Now it's going to tell me the same thing. I'm just going to skip that. I'm going to go to File, Load Configuration, and I'm going to load that ClearPath configuration. And that's it. That motor is now loaded. Okay, so let's check the other motor. And we can put the configuration into it too. I'll just do the same thing. So File, Load Configuration, Y-axis ClearPath configuration. And there we are. That one is now configured. Okay, that is the Y-axis done. Now I need to retune the X motor for the actual load that will be on the X gantry. And that is a little bit less than this. That's going to be, in addition to the Z-axis, about 30 pounds, not 40. So let me take 10 of these off. With the correct amount of weight on there, let me plug back in, and we'll retune this axis as the actual X-axis, and then just leave the configuration in the motor. Okay, that's that. Click Next, and I'm going to disable this motor next. And I do want to change the identity settings. And this one is going to be the Avid X-axis. And this one is done by tuning 30 pounds to the Z slide. Okay, and then I do want to save that. Now I'm not saving the configuration because I necessarily think that I'm going to need to copy this anywhere, but if anything happens, if I have to replace the motor, if it loses its settings somehow, I could potentially load this instead of retuning. Okay, that is for X. That's it for X. Next up is Z. Okay, I'm set up now to run the auto configuration for the Z axis. The difference here is I brought in a power supply so that I can deactivate the servo brake. If you saw the previous videos, then you know that I have a brake on the Z axis so that when the system is powered down, that brake locks it so that the weight of the spindle can't back drive the ball screw and cause the head to drop. I don't know if that's a huge consideration. I know on some machines that will happen, so I went ahead and included the brake in the design. Brake requires 24 volts to release, so I have a power supply here set to release it. And I'll go through the process and make sure that the motor is engaged first, then I'll release the brake, and then I'll re-engage the brake before releasing the motor. So let me start by plugging this in. And I will go through the same steps to auto-tune. Read and understood, yes. Testing stimuli is fine. Max velocity is fine. It does have limited rotation. And instead of moving the mechanics by hand, because this is vertical and suspended, I want to use power to move the mechanics. Now, the way this works, if I click and hold the control key, it activates the motor. So I will press and hold the control key, the motor's enabled, and now I will turn on the power supply to release the brake. And now I'll move it using the buttons here. So let me see, is clockwise go up or down? Clockwise goes down. So I'll just run this down through the full distance that it's safe to travel. And I know this axis is a little bit sticky down near the bottom, so I'm going to go ahead and run it as low as I can. I believe I have clearance to go about 8 inches with this weight plate, and I believe the total travel of the axis is 8.5. So we'll just go to there. Now, I am going to keep holding the control key when I click next, and that will leave the motor enabled. Now I can release it, peak torque 100%, no limit, 19.1 revolutions, and just click next. Warning, you may hear noises. Next, and click run, and hover near the escape key. Okay, that's done. Click next. And I am going to jog the position counterclockwise to take it back up. And now that I'm near the top, I will deactivate and relock the brake, and then I will click disable. Okay, that's done. I want to change the identity settings. And this is 30 pounds, and click OK. And same as the others, I will go ahead and save that. Okay, it's all tuned. Let's power it up and see it run. Make sure we didn't totally screw it up so it doesn't work at all. Okay. Okay, it does seem to move. Let's give it a rapid move all the way back to, let's see, go to the machine XY0. Nice. Now, one thing that I'm noticing here is that the sound is a little bit different. I don't know how to describe it, maybe a little bit sharper. That TIE fighter sound when the thing's traversing seems just a little bit more pronounced. And I hear ever so slightly a little bit of high-pitched whistle right after it stops in position. It stops after maybe a half second. And I suspect what's going on is now that the motors are tuned, they are much more aggressively maintaining position. And that's, I think, what I want for a CNC machine. It doesn't bother me. We'll see over time if I need to move the fine-tuning slider. But for now, I think I've got it tuned. I think everything is running about as well as it can. We'll do some more testing in the future, but coming up next, we need to get a spindle on this thing, get rid of these plates, and get it wired up and get everything trued and adjusted, and then make some test cuts. And that will all be coming up in the future. If you enjoyed this video, give it a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.